Okay, well, I hit update and bad things happened. Okay, so, hello, my name is Scott Grizzard. This is Discrete Math. I'm from the University of South Florida. This is the 29th of September, and we will try this once more with feeling. Hitting the button apparently made it go a little nutty. There's also a new OBS version out today, so it wanted me to update, but I didn't. So it should still work. So we'll try the update for OBS tomorrow. Okay, so let's try this again. How's everybody doing? All right, so as usual, we have chat in Twitch over there, and we have chat in Discord. Reminder, everything on Twitch is public. Discord is reserved to the class. And are there any other questions? Okay. So we had a mostly review quiz. There was some new stuff, but the big thing I wanted you to get down was that I noticed some of you still don't have the binomial theorem. So I'm just basically going to keep asking the question until until most people get it right. Well, most people are getting it right. I'm going to keep asking the question until the number of people getting it wrong is few and far between. Let's go over the quiz. Excuse me. So AB cubed. So I've got A plus B cubed. And that, by the binomial theorem, is 3 choose 0, A cubed, B to the 0, plus 3 choose 1, A squared, B to the first, plus 3 choose 2, A to the first, B to squared, plus 3 choose 3, A to the 0, B cubed, according to the binomial theorem, and that is that one right there. This is, of course, the expansion for the fourth. This is nonsense. This one is nonsense. This one is nonsense. And then, of course, this equals 1 times A cubed B to the 0 plus 3A squared B to the first plus 3 A to the first B squared plus 1 times A to the 0 B cubed. And that's that one. Okay, how do we feel about that one, 1 to 5? Okay, so someone's saying that apparently it marked you incorrect. I will look. That is very strange. It should have marked those as correct. If it did not, I will have to fix it. I don't know if that's true. Someone's saying professional streamer wasn't part of the job description. That is correct. But I'm learning. Okay. All right, this next one. Let S be the successor of N, the successor function for all the natural numbers. The successor of every natural number is in the natural numbers. That is true. The key here was figuring out what this was saying. Someone's asking about how do I get the coefficients. I can use Pascal's triangle, but recall that N choose K equals N falls K over K factorial. So 3 choose 0 equals 3 falls nothing over 0 factorial. So there's only one way to sort one element, and there's only one way to draw nothing, right? So if I take my cards, 3 falls 0 would be the number of ways to draw three things where order matters. I'm sorry, 3 falls 0 would be the way to draw, from a set of 3, would be the way to draw 0 items where order matters. Well, if I'm drawing 0 items, there's only one way to do that, correct? If I'm trying to draw 0 items from 3, there's only one way to do that. This one is nonsense because of this right here. So 3 false 2 equals 6. And this one is missing the factorial underneath. Okay? So if I did this, if I did AB cubed, right? If I did this here, it would be... I'll just go through them. So this right here is 1 over 1. 3 choose 1 equals 3 falls 1 over 1 factorial, which equals 3 over 1, which equals 3. 3 falls 2 equals 3. 3 choose 2 equals 3 falls 2 over 2 factorial, which equals 3 times 2 over 2 times 1, which equals 3. And 3 choose 3, that just equals 1. I'm not going to do it all out, but it is. Someone's saying nice one, Scott. Did I mess that up? Maybe I messed something up. I don't know. I don't think so. So yeah, you could have... So this one's missing. If I had written here 3 falls 0 over 0 factorial a cubed b is the 0 plus da-da-da, that would have been correct. But I didn't. Right? This is missing the factorial term underneath. This is nonsense. This is clearly incorrect. This is missing the coefficients. That is missing the coefficients. Okay. So let me just say then, people seem a little bit confused about this. So let me go back here because it's really important. 0 false 3 is nonsense. I can't spell nonsense. Something like that. There we go. So 0 false 3 is nonsense. Okay, this is the expansion for a plus b to the 4th. This one is missing the factorials. This is nonsense. This is just wrong. This is just wrong. This is missing the coefficients. And this is just wrong. Right, I can't choose 3 elements from a set of 0 size. These things are actually defined. You extend the things, but you wind up with different numbers. Okay. This is the symbol for the set of all integers. That is true. This says Q is a subset of Z. That is false. 1/2 is not an integer. This is true. This is the definition of the rational numbers. And this is true. This is the property of distributivity. Okay. So what I've described here is the set of fractions on the integers. Okay, so I've got, for example, 0 over 1 is n, negative 5 over 3. All of these are rational numbers. 4 halves, which is 2. All of these are rational numbers. 2 over 1, 7 over 65. All of those are rational numbers. N is not. So n cannot be 0. And remember, for us, 0 is a natural number. What did I say last time? Did I mess that up last time? It is totally possible that I did that. Because it depends whether or not you say 0 is a natural number. No, I said positive integer. Okay. So, yeah. It depends on whether or not you say 0 is a natural number or not. Since we said 0 was a natural number, we can't include 0 in the bottom. In other textbooks, you'll see that the rational numbers are defined as p over q, where p is an integer and q is a natural number, but they're not including 0 in natural numbers. So again, we're kind of sticking to the idea of programming, and programming, normally you include 0. Okay. So this Q means the set of rational numbers. Those that are ratios of integers, of course, getting rid of the 0 on the bottom. So how do we feel about those, 1 to 5? Okay. So think valid integer fractions. Okay. I think if you put in 2 right answers and 1 wrong answer, the system gives you partial credit, but I'm not sure, because it has a add and then subtract thing that it does. Name one thing you found memorable from the previous lecture. As I said, I'm not sure exactly how the grading thing works on Canvas for those. I do know that they give partial credit, but there is a penalty for choosing something that is incorrect. And I haven't played with it sufficiently to make sure. Okay. But it is the tool we have, so I have to go along with whatever it wants in one sense, because it is the tool we have. Okay. Okay. So last time we talked about oops. Come on. There you go. So last time we talked about the exponential thing as a function. And we talked about kind of an algorithm to do exponentiation. And we also defined the integers and the rational numbers. And I messed up because I didn't remember that you had to define a predecessor function in order to do subtraction. So we'll do that today. But remember, I mentioned this idea that what you had to do is you had to bootstrap the operations, because you had them defined with algorithms on the positive number or the natural numbers, and then you had to go back and you had to define. So anyway, you're supposed to define And then you're supposed to extend addition to include all the integers. And then you have to extend it to include the rational numbers. And you have to extend multiplication and all that. We're not going to go through it, but basically what I did wrong was I didn't define subtraction first. Because that's what you have to do in order to do the addition for the integers. So you have to define the predecessor function first. We'll do that today. And then we also defined what we meant by the integers and rational numbers. And then we had this weird proof that 0 can't have a multiplicative inverse. Because if 0 has a multiplicative inverse, we end up with the situation where 1 equals 2, where we care about the properties, right? So if we have distribution, commutativity, and associativity, we wind up breaking it the minute that we try to define a multiplicative inverse for 0. It can be done as long as you don't care about the properties. So you can set up special rules where 1 over 0 and 2 over 0 are both infinity, but you have to set up special rules that break the properties of commutativity, distribution, that sort of thing. And you could sort of get most of it back, but you do break some rules. All right. So that was that's what we did last time. Are there any questions about that? Okay. So today what we want to do is we want to talk about proofs by contradiction. So what we want to talk about was and we're going to do the famous one. So here's what it comes down to. When a mathematician says something is true, okay, we're not like a social science. We don't say, true. We can say true almost all the time, or almost everywhere. But when we do so, we have a precise definition of that almost everywhere. So when we say things are true, when we say that for every triangle, a squared plus b squared equals c squared, we mean for every triangle that meets the properties, right? We mean every time. There's not some like triangle with a special exception that is on the Euclidean plane that is a triangle, right? If it's there's not some wandering around. Oh, except in this case, no. When we say every triangle, every flat triangle on the Euclidean plane, the angles add up to 180 degrees. And when we say that a squared plus b squared equals c squared, we mean for every, which has this interesting thought. Okay? When we say for every, we mean for every. When we say something is true, we mean it's true always. And that has an interesting consequence. That means if a statement is not true, the statement is false. We only have two options. We don't have true, false, and maybe. We have true and false. So in math, if something is not true, then it is false. There is no maybe in our logic, okay? Now, you can say things are true for some instances of this, but not for others. But then what you're going to sit down is try to find out what the instances are where it's true, and then you make statements about that as a class of objects, okay? So that, but as a consequence, when we say something is, we have this idea of an excluded middle. That's what that's called, the excluded middle. And we also have this other interesting thing. We have a couple rules of inference. For instance, if P implies Q, then Q, not Q, implies not P. This is modus tollens. Okay? So let's say my system has a contradiction. suppose P and not P are both true. Okay? Let R be the proposition the moon is made of green cheese. Is everyone on board with that? 1 to 5, how do we feel about that? I've got two things that are both, I've got P and not P both being true, and I've got this proposition R, and I'm saying nothing about R, but I'm simply saying I'm saying that R is the proposition the moon is made of green cheese. Now, from P and not P both being true, I'm going to prove to you that the moon is made out of green cheese. So R implies, let's just say, either the moon is made out of green cheese, or let's say that P is true, or the moon is not made out of green cheese. Does everyone see how this follows from P? Okay, so if I take the statement, this card is the 8 of diamonds. Okay, that statement is true. Then the statement, this card is the 8 of diamonds, or this card is the Queen of Spades, is also true. Does everyone see that? 1 to 5, how do we feel about that? If I say that if this card happens to be the 8 of diamonds, then the statement that this card is the 8 of diamonds or this card is the Queen of Spades is true together. Okay. All right. Well, P or not Q, that's equivalent. I'm sorry, P or not R, that is the exact same statement as R implies P. If the moon is made out of green cheese, then this card is the 8 of diamonds. Perfectly valid. But that means that not P implies not Q. Well, since not P is true, I'm sorry, not P, implies not R. I screwed this up. This was supposed to be this. Sorry about that. This was supposed to be the Queen of Diamonds. This card is the King of 8 of Diamonds, or not. This is the moon is made out of green cheese. That makes this not that. Not R implies P. Yes. Sorry about that. So not R implies P means that not P implies R. Okay. But this here means, did I do this right? Yes. Okay. So that means that not P implies not R, which means that not P implies R. I should probably include these little steps in between. This is why I messed it up, because I didn't include the steps. So this was P or R. So this became P or not R. That becomes not P implies Q, which now becomes not P implies not R, which becomes not P implies R. But since not P is true, that means R is true, and the moon is made out of green cheese. One to five, how do we feel about that? No, the blue text is not replacing. The blue is just the intermediate steps. Right? I start with the idea that P is true and not P is true. So I started with a contradiction. Right? That means P is true. Which means P or R is true. Which means that P or not R is true. Which means that P or not R is true. Which means not P nor R implies P. Right? But the point is, if I have a contradiction, my system will prove anything. And this is not very useful. Okay? All right, so people seem uncomfortable with this. Let's go through the steps. Okay? Let P and not P be true. Okay? Let R be some nonsense. Okay? I'm going to show from this that R is true. All right, since P is true, P or R is true. So P or not R is true. So P or not R is true. Implying, right, by the equivalence, this is not R implies P. Then not P implies, implying not R implies P. That means not P implies not R, which is the same as not P implies R. Since not P is true, R is true. Okay, so now how do we feel about it 1 to 5? Exactly. So someone's pointed out that saying P and not P are both true at the same time is nonsense. Yes, but that's the point. So the method of contradiction is as follows. This is called reductio ad absurdum. Right? And that's the point. If I come up with nonsense, this is called reductio ad absurdum. And it is a valid rule of inference in mathematics. You take something to an absurd thing, which is a contradiction, and you wind up with that thing. So someone's asking about the Abbott and Costello routine. Who's on first? Sort of. Not really. But, yeah. So, I'm sure we could come up with a great one for that. Okay. By the way, the best ever Who's on First was done by, the original Abbott and Costello, but there was a great one with Ronald Reagan done by, what's his name? The old guy who used to host the Tonight Show. It was extremely funny, and he did it as Ronald Reagan. I don't remember his name now. But there was if you Google, if you YouTube Ronald Reagan, Who's on First Tonight Show, you'll find it. It was just absolutely hysterical. Okay. So that's that green text to the right. Anyway. So what we want to talk about is the Carson. Yes, thank you. Jimmy Carson. Jimmy Carson? I think. Okay. All right. So the point is that if I could show something leads to two statements that are contradictions, the original statement must be false. Let's do an example. Okay. What we're going to do is prove the existence of irrational numbers. If we allow square roots, or roots in general, the inverse of exponentials, we create numbers that are not rational. The square root of 2 is an irrational number. And we want to talk about this, right? The Greeks wanted to talk about this too. Because if I have a triangle, a right triangle with sides of 1 and 1, then I get that 1 squared plus 1 squared equals, 1 equals equals 2, which means that there's some number here, so square root of 2 is the length of the hypotenuse of a right triangle whose sides are 1. Okay. All right. So let's prove this. And again, this is in your book. It's the classic proof. Okay? All right. So what I'm going to do is I'm going to assume otherwise. Okay? I'm going to assume there exists a rational number and I'm just going to assume that. I'm going to assume that square root of 2 is rational. Okay. So, if the square root of 2 is rational, then there exists positive integers. I'm going to say positive integers because the square root of 2 is positive, but you could just have an integer on top. There exists integer p and posant q so that the square root of 2 equals p over q, and p over q is the reduced form of square root of 2. So what do I mean by the reduced form? Okay? So just as I'll bring it back, but just as a little reminder, right? Reduced form means the following. Reduced form, 2 over 4 is not reduced. 1 over 2 is reduced. So when I say the reduced form, I mean there's no number that will divide both except 1. It says posant, positive integer. So how do we feel about that 1 to 5? If I've got a fraction, if I've got a form that's a fraction, right? There's some reduced form of that fraction. Yes, simplified. Okay. All right. So q times the square root of 2 equals p. Implying I'm going to square both sides. And I wind up with q squared times 2 equals p squared. Okay. Well, if that's true, then p squared must be even. So 1 to 5, how do we feel about that? P squared is even. P squared is 2 times some number. Okay. If P was odd, P times P, which equals P squared, would be odd. Since two odd numbers multiplied together are odd, is odd. Okay. So P must be even. How do we feel about this 1 to 5? If P was odd, if I take two numbers like 1 and 3, right? They form 3. If I take an odd number and multiply it by another odd number, I get an odd number. All right? Which means that P squared itself must be if P squared is even, P must have been even. Because odd times odd is odd, even times even is even. Well, if P is even, then there is an integer n so that P equals 2n. Right? I could divide by something. Right? It means that it's divisible by 2. If 4 is divisible by 2, right? It's 2 times 2. That's what it means, right? You give me an even number, there's some number that it's 2 times that number. That means q squared times 2, which is what I had before, equals p squared, which that means and p squared is 2 times n squared, which equals 2 times 2 times n times n. We'll just leave n squared there, right? So I've got 2 squared times 2. So 2 times q squared equals 2 times n squared. And I can cancel those 2's. Implying q squared equals 2n squared. Which means q squared is even. Okay. Well, q squared is even. If q was odd, q squared would be odd. So q is even. Now, what's the problem? What is the problem I've just created? Well, if Q is even, then there exists integer m so that Q equals 2m. I still don't have the problem. So P over Q equals 2n over 2m. Which equals n over m. What's the problem? What did I say was true about P over Q at the beginning? What is the problem? The problem is I said P over Q was the reduced form of square root of 2. But P over Q, n over m, equals P over Q. And n over m is more reduced. Right? So, or I could say, so P over Q was not the reduced form. And that's a contradiction. Because I divided through by the 2's. So the question is, how is this more reduced? Each could be P and Q were both even. I could reduce it by dividing out both the 2 on the top and the 2 on the bottom. And that contradicts my original assertion that P over Q was reduced. So I have two statements, right? I have two statements. R and not R are both true. And I can't do that. Therefore, the square root of 2 must be irrational. There's no fractional form for it. That's two whole numbers. Being. Okay. How do we feel about that 1 to 5? And notice I didn't start with much, right? I just kind of said, okay, well, if P over Q, if it is rational, then it has a reduced fractional form. That's all I really said. And then I showed it wasn't true. Okay. All right, so moving on, let's define the predecessor function. Okay. All right. Yes, Neverland. There you go. What I do is I explore Neverland and find a contradiction. Second star to the right. Remember that the dreams you planned really can't come true, etc. Okay. All right, so everyone's okay with the successor function business, right? All right, so let's go ahead and talk about this. For all n greater than 0, define the predecessor as equal to n minus n, where this is a set operation. Did I do that right? No, I've done this wrong. Crap. This should be the set containing n minus 1. But I want to say it without saying that. So if I take 0 and I set minus... would you guys please stop it with the moving GIFs? It's really distracting. I want this to be 2, so 2 is the set, and I want back the set just containing the empty set. So if I set minus, so this right here would be 2, it's just 2 minus the n minus 1. All right. I can't believe this. I worked this all out yesterday to make sure it worked. I don't know why I'm doing it wrong this time. So 2 minus the set 2n minus 1 equals the set 0 empty set, the set containing empty set, minus the set containing the empty set, which equals the set containing the empty set. Yeah, I'm going to put I think here. We'll post correction if not. I thought that was it, but I may have messed it up. So I'll post a correction if that's not it. Anyway, so once I've defined this, I define subtraction. So I define subtraction as, oh, right, because this doesn't work for omega. Okay, anyway. There's some way to make it work for the others. I don't remember how to, because it's not defined for omega. Yes, this is it. Okay, because it is defined for omega plus 1. All right. So it's not defined for 0 and it's not defined for omega. So the initial part of everything, right, is not defined. Okay, so I define substitution. I define subtraction the same way I did the as I did addition. So I have a loop, but I use the predecessor in the loop. But there's a key thing here. I can wind up in negative number territory. So to prevent that, I need to define the integers first. Okay, so I define the integers as I did, and then I define the predecessor p of 0 as equal to negative 1, the inverse of 1. So once I've done that, I can set it up so that I define subtraction as I did addition with an if statement in there if I run into the negatives. Okay, and it's way too detailed, but the point is I can define subtraction. Okay, Yeah, so I want to get to division. That's kind of where I was trying to get to. You have to define that. I shouldn't have even bothered. I should have just said, suppose subtraction is well defined. So suppose subtraction is well defined. Okay? So the point is I can define subtraction over the integers. So what am I going to do? Once you have subtraction, you can define division. But you're going to get back an ordered pair, not a number. Fine, I should say integer division. But you get back an ordered pair. Okay? So let's write out this algorithm we're talking about here. Here's what's going to happen. Let's say I want to divide I unplugged the card camera, didn't I? Oops. Okay. So let's say that I want to divide, let's plug back in the card camera. I was editing video earlier, but I needed the external drive thing. So let's do this. I want to divide, let's see, and now I need... I'm sitting here banging my hand on the desk, okay? So you can see me sitting here banging my head on the desk, right? Okay. Yeah. Go play Xbox. Okay. So what I want to do, I've got my cards, okay? What I want to do is I want to divide, let's say I want to divide 5 by 2, okay? So here's how it's going to work. Let's do 7. I want to do 7 divided by 2. So here's how it's going to work, okay? What I'm going to do is I'm going to subtract 2 repeatedly until I wind up with fewer than 2 cards. So this is 7 divided by 2 here. 1, 2, 1, 2, 1, 2, and I'm left with fewer than 2 cards. I've only got 1 card here now, okay? So I did 1, 2, 1, 2, 1, 2, and I've got 1 card left. So what I have is what I have is 3, remainder 1. Okay? So, let's write that out. So, suppose I want to divide 7 by 2. In other words, I'm doing 7 divided by 2. All right. Well, what I'm going to do is I'm going to have a loop. And the loop is going to subtract 2 until I run out. So what we're going to do is we're going to get n over k. Okay. Now, I'm going to do this. I'm going to do while. I'm going to have two piles, okay? I'm going to have the pile of cards where I do the thing. So I'm going to have a Q and an R. I'm going to have a quotient and a remainder. Okay? So, and then I'm going to have a remainder. Now I'm going to have a while loop. Okay, and the while loop is going to look like this. While while R, sorry, this should be, I'm going to define R as n. While R is less than, while R is greater than Q, and that should be greater than or equal to Q, or while Q is less than R, do the following. While R is greater than or equal to K, thank you. Do the following. All right, I'm going to take R, my new R is going to equal old R minus K. I'm going to increment Q. Okay, so what I've done is I've got my stack of 7 cards. Enter. Okay, and K was 2. That's what I'm dividing by. Now, I'm going to enter my loop. I do this right here is R equals R minus K. So now my new R is 5. I took 7, I divided by 2, and I assigned that to R. Then I had Q equals the old Q plus 1. So Q now equals 1. And now I redo the loop. Right? So I loop since R since 5 is greater than 2. So I enter it again. R now equals R minus K. So R equals 5 minus 2, which equals 3. And Q now equals 2. Loop since 3 is greater than 2. Now, R equals 3 minus 2, which equals 1. Q equals 3, end loop. Since 1 is not greater than 3. Since it is not the case that 1 is greater than 3. Okay. So I do this while I get there and I loop. Now what I'm going to return, I'm going to return the ordered pair Q R. So I get a quotient and a remainder. 1 to 5. How do we feel about this? Oh, yes. 1 is greater than 2. Yes. So I should put here k. Since I did this here, I put while r is greater than k. And it should be r is greater than or equal to k. So this should be k is less than r. Well, yes, k is less than r. All right, so the idea was simple, but hard. Simple, but hard. I take a stack of cards. Let's say I want to divide 10 by, let's say 12 by, no, that would divide evenly. 13 by 3, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I want to divide 13 by 3. So what I'm going to start with, right? I've got 13 cards here. Loop. 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 I've got 4 stacks of cards. I incremented 1, 2, 3, 4, and I've got a remainder of 1. Okay. Okay. And that's the division algorithm. Now, in PHP and in almost every programming thing, there is something called the modulus algorithm. There's something called the modulus operator. And the modulus operator gives the remainder. Okay. Gives the remainder from the division algorithm. For example, and it's almost universally done with a percent sign. So, for example, 13 modulus 3 equals 1. If I divide 13 by 3, I wind up with a 1. Okay? Yes. So 13.3 under division, since division 13.3 returns 4, 1. So this gives the remainder. So the modulus discards the 4 and only cares about the 1. Okay? Another example. 12 mod 3 equals 0. 5 mod 2 equals 1. 16 mod 6 equals 4, right? 16, I take off 6, I'm left with 10. I take off another 6, I'm left with 4. 4 is left. Okay? How do we feel about that idea, 1 to 5? Whatever this is, this gives me the remainder. And that's what modulus does. And in programming, it's universally the percent sign. Okay. Modulus. You can also see other notation is the word mod. So 13 mod 3 equals 1. Now, it's important to note that you sometimes see this notation. You also see this. You also see 13 is 1 mod 3. So these are the three common notations. I will usually stick to the percent sign. I not particularly like this because this gets into equivalence relations and we don't actually care. We're going to care about them a little bit later. So are there any questions about that? 1 to 5, how do we feel about that? I'm slightly over because I confused myself again. But I did do this one right. Okay, so we covered the modulus operator. Next time we'll get into GCD and the Euclidean algorithm. Okay, just as a reminder, yeah, so 13 over 3 should give you an ordered pair. So depends on the language. Most languages will give you a decimal answer back. Will convert integers to, not most languages. PHP will convert integers to float and give you a decimal back. There is an operation though to chop off the decimal. So you can write something to give you back the Q. And then the modulus operator is just always there. And then if you want both back at the same time, what you do is you write a little function that returns back an array. And that's actually the next problem set. So again, problem set 6, I moved to next week because we weren't kind of caught up. I decided to ditch a bunch of the rules of formal inference. So because I ditched that, we're going to get back on schedule. We just won't do the rules of form, which is fine. Then we'll get back to GCD and the Euclidean algorithm. Any other questions? Yes, so division would return an ordered pair. Exactly. Unrelated question. Okay, you can ask me about that. Okay, so what I've got for the next exercise, I'll post it probably tomorrow for the problem set. But remember, it's next week's problem set. Is you'll be given the division algorithm, and then I'm going to ask you to implement the Euclidean algorithm, which we're going to talk about next time. And then we'll start playing more with these modulus moduli because they're really, really cool, and they're kind of fundamental to what we're about to do in number theory. Any other questions? And then we'll start playing with that. Okay. I'm glad you enjoyed the lecture. Some people did. Excellent. I like that. And I will see you all next time. I will see you all on Thursday. Thank you.